brand new unit, and there is a few things that we didn't define in the KMT unit that we need to define first before we jump into the math. The gas law unit is pretty much all math problems again, so we kind of sidestepped from that for a little bit, and we went into the math problems. We stepped away from the math problems, we got into the vocabulary, and now we're back to the math where we're going to apply a lot of the different things that we talked about with the kinetic molecular theory just in terms of gases. So we talked about the kinetic molecular theory, the movement of molecules with gases, and then we talked about liquids, and now we talked about solids. We're only going to focus in on gases. Gases have very predictable behaviors because of their properties according to the kinetic molecular theory. So the first thing that we need to define that you might have seen kind of interchangeably used last unit is the word gas versus the word vapor. Now they are both in the same state of matter. They're both a gas. It just depends on what state of matter they're in at room temperature, which actually it's not even room temperature, it's actually STP, standard temperature and standard pressure. So if you have a gas, like something that says you have oxygen gas, helium gas, hydrogen gas, what that means is at STP, which I'll define on the next slide, at STP, if you have something that's called a gas, it is in the gas state of matter at STP. So STP again is standard temperature pressure. I'll define that on the next slide. If something says that it's a vapor, something like water vapor, if it says a vapor, that means that at STP, it's a solid or a liquid. So they forced it into the gas state by changing the temperature or by changing the pressure, because remember, they're both temperature and pressure dependent for your state of matter. So there is a technical difference there. It just depends on what state of matter it is at STP. A gas is a gas at STP. A vapor is actually a solid or a liquid at STP. So now to define what that STP actually means, I just lost my little picture. I'm sorry. I will get that back right now. There we go. So if you have anything that is at STP, that means that you are at a standard temperature and a standard pressure. So not Stone Temple Pilots, not the oil brand. STP actually stands for standard temperature and pressure. So standard temperature is one value, standard pressure is a different value. When you put it together, it's called STP. Now those values that you're going to use for STP, standard temperature is 0 degrees Celsius. So we'll have to convert to Kelvin like we're going to talk about here in a little bit, but standard temperature is 0 degrees Celsius. Standard pressure is 1 atm, which is about what we're at here in Houston. We're a hair higher than that because we're not quite at sea level. But standard temperature and pressure, anytime you see that value, it is 1 atm for your pressure and 0 degrees Celsius, so colder than room temperature. And when we look at our gases throughout this unit, we are going to look at the pressure, we're going to look at the temperature, and we're going to look at the volume. And we're going to manipulate those values. In class, we're going to make a little card. So you might want to take like a piece of paper or something and you're going to write PTV on it. With this card with PTV, P is pressure, T is temperature, and your V is your volume. So we're going to change the pressure, we're going to change the temperature, we're going to change the volume, and we're going to see how the other values react to the pressure, the temperature, the volume changes. Now with your units, when we go through these, we are always going to use ATM or atmospheres for your pressure. So if you don't have ATM or atmospheres for your pressure, we're going to have to use those conversions to get that. Temperature is always in Kelvin, so if you don't have your temperature in Kelvin, you're going to have to use that. So you're going to have to use Kelvin. And then your volume, you're always going to use liters. So if you don't have liters, we're going to have to go from like milliliters to liters, the most common volume conversion that you're going to have. They do need to be written in this order for your PTV. So you have pressure, temperature, volume. PTV like MTV. You guys probably don't know that MTV stands for music television, but we have PTV, pressure, temperature, volume in that order. When we are looking at these things, we are looking at the amount of the gas. How many particles are there? And when we look at these changes with the pressure versus the temperature, or with the volume versus the pressure, or whatever else, the amount, how many particles are in the sample, is going to remain constant. So if you have 1 mole of gas, you have 1 mole of gas through the whole math problem. That's going to remain constant no matter what. We're not going to lose particles. We're not going to add particles to our sample, because that's going to affect the pressure, the temperature, the volume also. So for right now, if you have 4 grams of a gas, you have 4 grams of a gas through the whole thing. If you have 5 moles, you have 5 moles through the whole thing. So the number of particles that are in your sample will remain constant through the entire math problem. So I've already kind of alluded to this, that when you are doing the math problems themselves, anytime you have a pressure, you're going to convert it to ATM. If you don't have ATM, you're going to convert it out so you do. Anytime you have temperature, you have to use Kelvin. So a lot of times you're going to be given Celsius, you're going to have to convert it to Kelvin. And then your volume is always going to be in liters. So ATM, Kelvin, liters are the units that you have to use for your math problems, that as we go through the gas law equations, you're going to have to convert to those 3. Those are the magic 3. And so when we do these math problems, you get the correct units. We're going to have 5 main types of algebraic types of problems that we're going to do. You have your Boyle's law, you have Charles' law, you have Gay-Lussac's law, where it's going to look at 2 different variables, pressure versus volume, pressure versus temperature, volume versus temperature, and we're going to see how they are affected. Then we're going to put all 3 of those together in something called the combined gas law. And then we're going to have something called the ideal gas law, that we're going to look at the behavior of ideal gases. So as we go through this unit, just a little bit of vocabulary to start us off. We're going to jump into the math after this video. We're going to look at Boyle's law first, and then Charles, then Gay-Lussac, or people say Gay-Lussac. I don't know, I've always heard it Gay-Lussac, but in the last few years I've heard, because he is French, it would be Guy, but who knows. I'm sure that it's probably right. But anyways, then we're going to combine them together. And then after we come back from spring break, we will have the ideal gas law. So we'll have these gas laws first. We'll end up with some gas stoichiometry, and then that'll be your whole unit pretty much. So stick around. We have another video after this on Boyle's law. Have a good day.